I've always believed it is important to have a sense of magnitude when it comes to economics. If you're anything like me, you may have wondered how many solar panels would you need to match the electricity production of one nuclear power plant? Well, that is the question we'll explore today. A typical nuclear reactor has the installed capacity of 1 gigawatt, that is 1 billion watts. Installed capacity is the maximum potential output. Power plants usually have 2 or 4 such reactors, combining to a total of 2 or 4 gigawatts, even though the largest one, Japanese Kashiwazaki plant, has 8 gigawatts. The maximum output of residential solar panels mostly ranges between 200 and 500 watts. For the purpose of this calculation, we will take the rather generous estimate of 400 watts. So how many such panels would you need to match the moderate 2 gigawatt power plant just in terms of the installed capacity? The answer is 5 million. For the larger power plant, it would be 10 million panels. But that is just the beginning of this calculation. The second step is to include the capacity factor. The capacity factor is the ratio of actual output over a year to the maximum potential output. If a plant produced at maximum output 24 hours a day, 365 days a year, its capacity factor would be 100%. Nuclear power plants have by far the highest capacity factor, reaching over 90%. With solars, it's very different. During the night, the output of solar panels is essentially zero. On dark, cloudy days, the production is also substantially limited. When the surface of the panel gets overheated, its efficiency also decreases, so it may not produce at 100% of its potential, even on very hot summer days. Lastly, the panels are degraded over time by various factors, meaning their efficiency goes down with age, typically by half a percentage point per year or more. So by the end of its 25 to 30-year lifespan, its efficiency may be down to little over 80%. Therefore, solar panels have the worst capacity factor of all energy sources. Some websites claim that it is almost 25%. But that is true only for the top locations in sunny regions, such as California, Northern Africa or the Middle East, as you can see on this map of photovoltaic power potential. You can also see that Middle and Northern Europe, which pushes renewable energy the hardest, is also one of the worst places on Earth for solars, even worse than Northern Canada, despite its higher latitude. Write down in the comments why do you think this is the case. But the global average capacity factor seems to be around 16%. Back to the calculation. So you would need 5 million solar panels just to match the installed capacity of one moderate nuclear power plant. But given that even in suitable locations, the capacity factor of photovoltaics is almost 4 times lower than that of nuclear power, you would need 20 million panels to actually produce the same amount of electricity across a year. If we take the global average capacity factor for PV, the number is closer to 28 million. In Germany, where the capacity factor is only a meager 10 to 12%, the corresponding number would be over 40 million. And in Sweden, the land that so generously exported Greta Thunberg, the capacity factor is barely 8%, so you would need incredible 55 million panels. Of course, if you compare it with a larger 4 gigawatt nuclear power plant, the number would soar to more than 100 million. Hence the thumbnail. This of course does not account for the problem of volatility of the production. Without a next-generation battery technology and massive storage capacity buildup, those tens of millions of panels would still be useless during the night and certain dark days, but would overproduce on sunny summer days to the point of causing a blackout. Next time, I will compare nuclear and wind energy. Let me know if you would like a comparison of costs and material required to produce the power plants. Until then, stay unconventional.